Yeah, so this is kind of a 15-minute check-in on a project that is in year 1 of 3 now called Open Source Computing for Science Education. What I'd like to do is put it in context with some other initiatives that are underway at UBC, connect it to Pangeo through the kind of Pythia graduate education wing, and then give a few lessons learned. We talked, we mentioned workflow, I think, in the last meeting. And so I just wanted to say a little bit about workflow and infrastructure for making this all go. And then what we're planning for this summer and for the next 5 years. How are you going to grow and sustain an effort to bring computer-based instruction to graduate and undergraduate education? So first, just who are we? US is a big department. We've got 600 undergraduates. We've got kind of a mini United Nations of faculty. So we span pretty much every discipline in earth sciences at various levels of engagement with computation, right? Hard rock geologists, marine biologists, but also people who are running jobs on 2000 cores, and we're doing real-time forecasting for both the Salish Sea and for mountain weather at high resolution for commercial clients. So we've got a really great kind of test bed for how you introduce these new computational concepts into sort of faculty student population with a whole variety of backgrounds. We've been teaching web-based Python courses for, since the turn of the century. And so that, and the fact that we've got our own 1000-core InfiniBand cluster, we've got 2 petabytes under RAID, we've got a whole bunch of clusters that are aging out and provide sort of free 8-core, 15-gig nodes for a lot of instructional applications. 2 very talented Unix system administrators. So this gives us sort of the ability to do some kind of informal, kind of guerrilla-based projects that are very well suited for a university organizational structure, right? Where departments have a lot of leeway in what they kind of are interested in and undertake. UBC is it's no stranger to large-scale cloud Jupyter hubs. Syzygy, kind of a project led by Jim Colliander, who's on this call, is, so let me bring this up to date. So 36,000 students at greater than 20, I forget the number, universities, so federated Jupyter hubs. And this has meant that it's been a pretty easy sell at UBC to get them to, for example, hire 2 new software engineers and target 2,000 simultaneous users and 13,000 student accounts in the next couple of years. And then there's also a professional master's in data science. We get 1,400 applicants for 80 slots for that. We're introducing a new minor in data science starting this September. And this is big news, right? Because it removes kind of the Lisp Java blocker on our students to get into 3rd and 4th year computer science, and places it with an R Python stream, 6 new courses. And then we have a program, I'll let you click on the link, but quantitative something, I forget what this acronym was actually. It's a clever acronym. Anyway, we're rethinking quantitative education in environmental geoscience. So how do you get a common core of math, linear algebra, partial differential equations that you can use to unify teaching for hydrology and glaciology and physical oceanography and atmospheric science? What are the constraints? Well, a couple numbers here. 150, so that's the number of 3-credit student equivalents you need to teach to pay your salary with provincial help, right? And that was, for a geophysicist, that's a pretty big number. We're used to classes of 10 to 15 students. In Canada, salaries are 12 months. Federal research grant overhead is 15%, and it's very rare to see a grant tenure faculty member. So it really emphasizes the role of teaching at a large university in a way I think that's probably a little different from the American universities I'm familiar with, where a faculty member bringing in $1 million a year obviously more than covers their own costs, right? So the whole culture revolves more around teaching, I think, than in a typical R1 university in the States. Uh, Something that I don't think all my colleagues have internalized is that at replacement, right, you get one graduate student for a 30-year career. And what that means is that the graduate students are going somewhere besides academia, and they're learning things that you didn't learn just necessarily. And so preparing graduate students for the world outside of academia, I think is something where Pangeo is really poised to make a huge contribution, because you can see it in these meetings, right? The connections with the private sector and with applications outside of the university. 13, so that's the number of weeks in a UBC semester, not much time. And that means that you really have to think through how you're going to introduce a third or fourth year work study student to all of this technology. And it's extremely good discipline for teaching your own colleagues, right? How are you going to bring a busy professor who's programming in MATLAB into a new course, working with Git on a Jupyter Hub in Python, right? The materials to do that are not out there really. And so that's something that we're working to develop. And then, aside from the 150 students in a large undergraduate class, every student's going to need a portfolio, and every student's going to need capstone projects. And how to scale this to 30 to 50 students, again, is something where I think Jupyter and Jupyter Hubs offer some pretty obvious pathways so that we can give kind of independent sort of research opportunities to the median undergraduate student in a large department. So kind of the instructional philosophy of OCESE, this idea of top-down learning, scaffolding, and the spiral curriculum. So top-down learning, it's the way you read a research publication, right? You read the abstract, look at the conclusions, scan the figures. If it's interesting, I mean, maybe you have to go and learn ensemble Kalman filtering, but you get something out of the top and then you drill down. And again, scaffolding, starting with a dashboard in a large class in first year, revisiting those concepts. So you go from kind of just simple sort of windowed averaging to digital signal processing to Gaussian processes over the kind of career span of a student into graduate school. And you can use the same material, right? But you just augment it in a way that you can open up the black boxes. And then reproducible teaching. So there's a huge disconnect in my life between the way I do research with GitHub and continuous integration and pull requests, working with Markdown, and the way I do teaching on a learning management system. My colleagues are writing slides in PowerPoint, they're using DocX. It's the definition of high friction. And it's by design, right? There's private information on the LMS, there's solutions, but it goes every course. We cannot see anything really about 80% of the prereqs that our students are taking, aside from one page of learning objectives. There's major exceptions to that in stats and math that are completely open source. But by and large, this is a huge obstacle to making modular education work. The fact that you're sending students out to these courses and you don't have a clear idea of what learning objectives they're getting out there. So you need course material that's shareable, discoverable, and suitable for remixing. And this just shows you sort of the logistical problem that we're tackling here as we try and transform a whole range of courses. And we're doing it by paired teaching. So we have a plan to pair experienced teachers and then kind of a relay race where they hand off that particular skill set to a new teacher for the second time the course goes. And this is just a range of courses, large and small, oceanography, atmospheric science, data science, but pretty ambitious in that by the end of this, we should have a cohort of 15 to 20 faculty who are kind of Jupyter native, Python. Their graduate students themselves are familiar with Git. And I think with that kernel, then we can make this thing go long term. So how did year one go? We're very happy with the progress we made. We're running about 6 Jupyter hubs. We've used them for remote sensing course, environmental engineering, Brian Rose's climate physics course at the graduate level. We've pulled a bunch of students through capstone projects. CMIP 6 notebooks were a big hit. It was actually very easy to start with what's available in Pangeo and get a fourth year student going on sort of 3 different models with 2 different scenarios looking at internal variability or sea ice or that kind of thing. And then we're developing dashboards. We're pretty committed to dashboards because they're a good way to communicate with large classes, but also with administration, with outside funders, with our own colleagues, with people in other departments. Being able to run a low-cost dashboard and just watch things unfold turns out to be a huge advantage in almost proselytizing or evangelizing this material. Lessons learned, I'm a big fan of text-based notebooks, which means JupyterBook, MIST Markdown, JupyText. And what are the advantages? I mean, it's not hard to collect 75 notebooks for a 3-credit course. And if you're transitioning 10 of these courses, then you're up to 750 notebooks. And being able to recursively grep that material is just a huge advantage. Being able to convert the material from JSON to Python means that you can use pre-commit hooks when you check in to run, formatters, reorder your imports. MIST Sphinx allows you to organize 150 notebooks into a coherent Jupyter book that's cross-referenced, and that means your notebooks can be small, which is good, right? Again, you want this kind of remix culture, and being able to atomize your notebooks but still have this kind of big picture is a huge advantage. Jupyter books are static websites, which means they're cheap, and so anybody can browse them without having to spin them up, right? Or wait for GitHub to try and render them, which for our notebooks, 60% of the time it's not going to be able to because they use pretty exotic software stack, right? And Markdown and PyPercent means you can move easily between modules and notebooks. And so again, that keeps your notebook small, and it allows you to develop a core base of reusable components that you can share across a whole bunch of different applications. So what infrastructure is missing? So I think of this as the missing middle, right? We've got these nodes, single nodes. We're running Kubernetes on AWS, but that's overkill for a lot of these small projects, like these capstone projects. And so what we'd like the Pangeo stack in Docker containers running on the littlest Jupyter hub. And we aren't quite there yet, but I was really happy to discover Plasma. Again, I'll let you click on this. So QuantStack has developed this for French projects, but it's extensions to the littlest Jupyter hub that allow you to use Docker containers, and then CTS dashboards, which have been mentioned before, that allow you to actually move between Voila and Panel and Plotly Dash, which is, I think it's important to be able to kind of have a continuum of applications and then back up these student accounts we're using Restic, but it's not typically out there on the web, right? It's a lot of work to figure this stuff out yourself. And so I'm committed to kind of doing top-down learning for R systems, by which I mean writing kind of instructional material that, you start with Namecheap and DigitalOcean and Ansible, and everything just works, right? You learn Let's Encrypt and how to do routing to your various components and all the kind of stuff I've had to figure out on my own. So this will be interesting. I'm looking for beta testers as I gradually push this stuff out there, and I'll be reporting back. What are we doing this year? So Lindsay Hagee, who many of you know, is going to be teaching Data Science 100 in September in R, but at the same time, we're working on the Python translation and moving the R Markdown and R from the stats course to produce a section of Python, which is going to grow, right? We expect 2,000 students in first year data science in a couple years. We're Pythonizing some of our MATLAB courses. I'm wrapping libRadTran, which is a 250,000 line piece of C that's used extensively for atmospheric correction and for inverse remote sensing problems, wrapping that in a dashboard for our third year climate course, where we spend a lot of time with, CO2, 15 micron absorption band and that kind of stuff. We're writing a new CMIP6 model browser that's Plotly Dash based on X-ray and Dask intake. And we're funding an experiment in paired programming with Rowan Coquette, who some of you know, who has a startup called CurveNote that does collaborative programming on Jupyter books. We're going to try that out in our large second year programming course in the fall. So what are the next steps? Well, I'm interested to see whether other people are in my situation with single node kind of Docker-based hubs. I think we should be thinking about how we organize graduate courses, projects, case studies in the whole kind of earth sciences computation kind of ecosystem. Really interested in strengthening pathways for graduate students to work as domain experts in the private sector, because that is the future, and we don't have those connections at the level that I'd like right now. And then something that came up, I think, 2 meetings ago, SimLab, and Brian Rose talked about opening up the single column API maybe to drive kind of SimLab-based climate modeling modules. I mean, that's right up our alley, and we'd be really interested in collaborating on that. I'll stop. 18 minutes. Sorry about that.